the surface, the floor area of all your floors, and the total amount you fill it in this cell. Then you calculate the number of floors you have. It's including the ground floor, of course. So in my first 2 detached houses, I would fill in 100 square meter here, and the number of floors would be 1. In my terraced house that we have analyzed, I would say here 150 square meters. And I have 3 floors, 1 on the ground floor and 2 higher levels. Then I calculate for a floor, one typical floor, the perimeter. So not for all floors this time. I just calculate the perimeter of one typical floor. If you have very different floors, you can also calculate it for all floors and then divide it by the number of floors to have an average perimeter per floor. The same you do for the length of the internal walls. So you calculate what the length is of the internal walls on one floor, which can be representative for all the floors, or if you don't have such a floor, you calculate the length of all internal floors on your building and divide it by the number of floors to have an average number. There are different or other things that we need to fill in for a cost calculation at neighborhood level, but that is for the next module on costs at neighborhood scale. Now, once you have these data, these are the data that you need to measure first for your projects. Once you have these, we can calculate the ratios of the different elements and we can extract a simplified box building. How do we do that? Well, first of all, to draw this simplified box building, we need to calculate an equivalent width and an equivalent depth. So it's the width and the depth of our box building with a rectangular floor plan. We can also calculate then the ratio between the two, so the width divided by the depth as additional information, and we can calculate an equivalent perimeter, an equivalent length of a room, an average room. If assuming that all the rooms are rectangular rooms, then we can calculate an equivalent length of the side of such room, and we can calculate the equivalent surface area of these rectangular indoor rooms, but I'll come back to that. So first of all, we want to calculate or define an equivalent box building for which all the ratios are identical to the ones of our existing building. So what we will do is we keep the number of floors identical to be sure that we have the same ratio of ground floor, roof and intermediate floors. But what we need to do now is we need to determine the width and the depth of that rectangular building so that also the ratio of the external wall is identical to the ratio of the external wall of my real building. So what we know the floor area of one floor, because we have measured it. We know the perimeter of one floor, because you also need to measure that. Once you know these two, what we now want to calculate is a rectangular with a certain width and depth, what we call equivalent width and depth, so that the area of this rectangle is the same as the floor area of one floor in your building. So the floor area of a rectangular building is calculated by multiplying the width by the depth. And the perimeter of my rectangular should be the same as the perimeter of my real building. Well, the perimeter here equals 2 times the width plus 2 times the depth. So here we can define, so we have 2 formulas. And we know the area as we have measured it, it should be identical, and we know the perimeter as we have measured it. So we have 2 unknown variables and we have 2 equations, meaning that we can solve it. We can these 2 equations and determine the values of these 2 variables. From equation 2, we can take out the width and say the width is your perimeter divided by 2 minus the depth. And then we know the perimeter, but we don't know the depth yet. From equation A, we can then fill in the width here by this formula. So the width is replaced and it's equal to the perimeter divided by 2 minus the depth multiplied with the depth. The area and the perimeter we know, as these should be exactly the same as our real building. So we can fill in the values of our real building here. By doing that, we can determine the depth of our building, because that's the only parameter we don't know. So the area equals the perimeter divided by 2 multiplied with the depth, that's the first part, minus the depth multiplied with the depth is the depth square. If we calculate it further, we see that we have this formula. So the depth to the square minus the perimeter divided by 2 multiplied with the depth plus the area equals 0. So this is the formula we obtain. You can solve this formula. You can solve this formula in this way. Here it is explained how it's done. I will not go into detail, but if you work it out, you will see that you can calculate the depth and you can also calculate the width with the other formula we had on the previous slides. So by calculating this, you know all the parameters, you know the perimeter, you know the area, you know the perimeter, you can solve it and you can calculate the depth of your building, and equally you can calculate the width of your building. And as such, you have determined the two parameters for your equivalent box building, and you can draw it on one of the grids that are provided on Toledo. Secondly, we want also to subdivide our building, our box building, with rooms. So we want to give it rooms, and we will give it internal rooms in such a way that the length of the internal walls of your real building are equal to the length of the walls in your equivalent box building per square meter floor area. The rooms that we will design in the box building will all be square rooms as a simplification. So what we now need to know is, first of all, what is the length of the internal walls in the real building. So you calculate the running meter of the internal walls on one specific floor, which is representative for your case, or you calculate it for all floors and divide it by the number of floors to have an average length per square meter floor for one floor. This is what you have to measure, and based on that, we will calculate two things. First of all, we will calculate the equivalent length of one side of a square room, assuming that your full building is subdivided in square rooms with that specific length. And then we will calculate the area of such room, such a square room. So what we actually will do is subdivide the equivalent box buildings in rooms which all are squares and which all have the same size. The area of one such room we call the equivalent surface of, so if I go back, it's the equivalent area of one square room, and the side length is the equivalent length of the side of the square room. So it's the ESRS. Now, how can we calculate the length of such sides, and how can we calculate the area of such room? Well, we know that the number of the amount of the number of the square rooms equals the total floor area of one floor divided by the area of one inner space, as they are all the same. And we know that the length of such square room equals the root of the area. Now, if we subdivide our total box building by these different rooms and we calculate the length of all the walls surrounding these square rooms, we know that the total length should be equal. So if we calculate all these lengths and we sum them up, the total length should be equal to the perimeter of the building plus the total internal length of my real building, of the internal walls of my real building, multiplied by 2, because I have 2 times this length, while I want to simplify it to 1 length. So I subdivide my box building into equal rooms, which are all square rooms, and I now want to calculate the length of the side of these rooms. Well, I know that if I look at this picture, that once I have subdivided my building in the number of rooms, and I know how many I have, I know my internal length of my real building, of the length of the internal walls. Well, if I then put them together, I can see that the internal length of my real building should be equal to this length. They should be exactly the same, because that's what I'm aiming for. I want to have the same ratios. Well, if I look at this picture, it is clear that the perimeter plus 2 times this length is what we have here, equals the sum of all the perimeters of these square rooms. Now, what we know is the number of rooms multiplied with the 4 sides multiplied with the length of one side is the total length of all these sides of the rooms. And that hence should be equal to the perimeter plus twice this internal length. Once we know that, we can start calculating, because the number of rooms equals, we calculated before, the floor area of one floor divided by the equivalent area of one square room. So then we know the number of rooms. We multiply it by 4 sides, and we multiply it with the length of one of these rooms, which equals the root of the surface. And that should be equal to the perimeter that we have calculated, plus 2 times the length of the internal walls of my real building. I hence have one formula with only one unknown parameter, and it's the area of the rectangular room, or the square rooms. So I can further solve the equation, and then I come up with this equation. The length of the square rooms, so one side, equals 4 times the total floor area of one floor, divided by the perimeter of that floor plus 2 times the internal walls of that floor. And once I know that, I can calculate, of course, the area, because it's just the side by multiplying by the other side. Now, to illustrate this, I assumed in this building that I have an internal wall length of 20 meters in total, subdivided somewhere in the floor plan. Well, if I now want to calculate or draw an equivalent box building with equal square rooms, where the total length of my internal walls for these square rooms equals the real internal wall length, I can calculate with the formulas from the previous slides these 2 lengths, the length of one room and then the area. And it's 5 meters, and then the area is 25. The same I can do for the second building. I have again an inner wall length of 20 meters, somewhere located in the building. the total length, so it can be different inner walls. I calculate the area, the length of the side of my square rooms, and I calculate the area, and I come to a square room of 19.75 square meters. And finally the same for the last example, where I again have 20 square meters, and I calculate the size of the side, the length of the side, and the area of the square rooms. Now, why is this so important? Because by drawing these different fictive square rooms, we can easily compare if the real building has a very large amount of inner walls or small amounts, looking at the area of these square rooms. Because, for example, we saw, if we look back first at the external walls, and then I go to the internal walls. If you look back at the external walls, and we assume that this is 1 meter, so we have a simplified example here, it means that this is 2 meters, so here I have a square building of 4 square meters. I have again the same building here, so I have 1, 2, 3, 4 meters, and it's 1 meter wide, so I have also a floor area of 4, in this case 4 square meters. We have seen before that the form determines the ratio of the external wall. So here we have 2 plus 2 plus 2 plus 2, 8 meters perimeter, divided by a floor area of 4 is a ratio of 2. That's the ratio of the length of the outer wall divided by the floor area. By changing the form, I see that my amount, my length of my external wall per square meter floor increases. So I have a less compact building. That I had shown before, that the size, or the layout, the form of my building, if the size doesn't change, has an influence on my amount of material and hence on my cost of my building. Now, instead of 1 large building, I could also build 4 small buildings. And the total of these 4 small buildings is the same as 1 large building. It's again 4 times 1 square meter, so I have the same floor surface when I add up the 4 buildings in B compared to the 1 big building in A, option A. Now the ratio of the outer walls is 4 times 4 divided by 1 is 4. So I have much more outer wall in this case than in the previous one, twice as much. So also the size determines the ratio or the amount of material per square meter floor area. Although the form is identical in this case, it's the size that also influences the ratio. So the same accounts for internal walls. We have seen this now for external walls, but it's exactly the same principle for internal walls. So if we look again at these different examples, and we have looked at before the outer wall and the amount in length per floor area, we knew that for the first example B it's 4. For the second example it was 2.5, and for the third example it was 2. Now, if we enlarge the building, but having the same form, we see that we can again get a different number, 1.33. If we look at the internal wall ratio, then we see that for the first one, we don't have any internal walls at all. So we compensate the fact that we had a lot of external walls by the fact that we have less internal walls. If the cost of both are identical, we might come to the same result as another building. But if the cost difference per unit of material of element is different between an outer wall and an inner wall, these different layouts will lead to different costs. Because in the second example we had a lower external wall than in the first, but we have now, of course, additional internal walls, and in total we have a length of 3 meters of internal wall compared to a floor area of 4 square meters. It's a ratio of internal walls of 0.75. For the example E, we have a large square building with an outer wall ratio in meter per square meter of 2, while we have now larger internal walls than the previous one. We have 4 meters per 4 square meters, or a ratio of 1 meter. Here we see that we have an equal amount of internal wall and outer wall per square meter of floor area. Now, not only the size of the building or the size of the internal rooms will determine the floor area, the ratios. Also the size. So this was the size that we had first. So we have smaller rooms or we have bigger rooms. If we have bigger rooms, so the size is 1.5 times this one. So here we have 1 meter, here we have 1.5 meter. We see that we have half of the amount of the internal walls compared to the first example. That's if we change the size. So if we have larger inner rooms, we see that we have less amount of internal wall. The ratio reduces. However, we could also decide to have 4 inner rooms, as we have here, 4 rooms, but now in a different shape. So here we have long, narrow rooms instead of more of the square rooms in the other example. Then we see now that we have the same surface of rooms, the areas of the rooms is identical, but by having more rectangular inner spaces, we see that we need more internal walls. So we see that the ratio of the internal walls increases due to this different form of the internal spaces. And so we can go on. We can make combinations of smaller and larger rooms, and more rectangular, or square room, or going to a square room, and then we see that we get different amounts of ratios, but I will not go into much detail here. This brings us to the final part, where we will now make our own calculations to estimate the investment cost of our buildings by, first of all, calculating the ratios. Once we have calculated the ratios, we can multiply it with the unit prices for each of the elements, and then we can calculate the investment cost of our building. So an Excel file has been developed so that you can make these calculations. Now, before we use the Excel file with the predefined calculations, the aim is first that you do it manually, so that you understand what's going on, what's being calculated. And we do that based on the examples given here in this session. So it will be exactly the same what you will do for your specific case. So what you will, the aim is that first of all, for your case, we draw an equivalent box building. We calculate the ratio of the floor and the roof, the ratio of the external and the internal walls, and we present them graphically. Based on these calculations, we will have an element table of your case with the specific ratios of the various building elements. And by then combining these with the prices per unit of element, we will calculate the cost of the building. So at the end, we will use fixed prices for all of you for each of the elements that occur in the building. We will only limit ourselves to a number of elements. We will not go in full detail. So we will have a look at several elements, calculate with the unit price, and then calculate the ratios for each of these elements. And these will, of course, be different for each of your projects. And so although we have the same prices for each of the elements assumed, you will see that due to the layout differences, the investment cost of the different buildings will be completely different. Now, to do that, there is a first part of this assignment 4 on the cost calculations of buildings. There is an Excel file on Toledo entitled Input and Calculation on Building Level. In this file, there are a number of gray cells which you need to input for your specific project. So it's calculating the floor area, it's calculating the parameter, it's calculating the internal wall length, and so on. And you fill them in the gray cells. Based on these gray cells, you calculate manually the green cells. Based on the green cells that you have calculated, you sketch the plan of one floor of your box building. So you determine based on the ratios the equivalent width and depth of this rectangular building, and also based on the length of the internal walls of your building, you draw the internal rooms, assuming that all of these are square rooms and the total length should be identical in your box building and in your real building. In addition, besides this box building, you will also make a graphical representation of the ratios of the roof, the floor on grade and the intermediate floors, the external walls and the internal walls, and you draw that on a cube of 1 cubic meter. You save, once you have filled in this Excel file and you have sketched the different ratios and the plan, you save it under your latitude, your building name, you mention building in the name, you mention again your country code, the city, and your specific name. And you hand it in the discussion board in the specific discussion session on cost of building. Now, in the discussion board, there is also an Excel file uploaded with an overview of the building cost of all the projects, and there you fill in your data for your specific case. So the different ratios of the different elements based on your calculations in this file. You submit everything by November 18th so that I can process it to give you feedback on what you did. So the outcome of this assignment is, on the one hand, your box building with the correct dimensions in line with your specific case and making sure that the ratios are identical. Also, you draw the rooms, the inner rooms, to have quadrant rooms, with the same inner length of the internal walls as in your real case. Besides that, you also calculate the ratios of the 5 elements of the ground floor, the intermediate floor, the roof, the external wall and the internal wall, and you draw them graphically. So you calculate them and you draw them. By doing this, you are able to calculate the ratios of different elements, and you are able to have a simplified box building and visualize this box building, also including the square rooms to have an equivalent length of internal walls and visualize these. Moreover, you are able to elaborate on the macro element level an element table with the different ratios of the elements. And with this slide, I would like to end this part of the session on costs of buildings.